Hey there, ladies and gentlemen, boys and girls. Mr. Richardson here. I'm going to use this video. I'm going to get into it pretty quickly about going over some force diagrams on our practice here. So I'm going to go through a couple examples here. Actually, I'm going to go through all of them here. Just talk about out loud the thinking through the process. So if you're using this video to kind of check over your answers, you can skip ahead to the video. I'm going to just go in order 1, 2, 3, 4, 5, so on and so forth. Find the problem you have. I'm going to walk through it. I encourage you to walk not just to the answer, but listen to the whole problem so I can talk about the thinking process. So, the big part of going through these force diagrams is thinking about what is happening. Right? What forces what objects are interacting with the object that it could be creating a force? Are the forces balanced? Are they unbalanced? So should the arrows be equal, unequal? Should they be up, down, left, right? These are all things I'm going to kind of think out loud about. So nice thing about this video is if you struggle with one of the questions and you didn't understand it, try and listen or watch it again, listen to it again. Again, I'm going to try and think through it as best I can, but we got to pull on a lot of the things that we already have talked about. So let's go ahead and get started here. All right, we're going to start with number 1. All right, so number 1 here, we're thinking about the lamp. All right, and we know that the lamp is resting on the table and is not moving, that means we immediately know that we're going at constant velocity, which already means we know that we're going to have balanced forces. So whatever force diagram we show for the lamp, overall, the forces between them should be balanced. And since we're not going to use numbers, we are going to use the length of the arrows to indicate how much force, and they should balance each other out. So I always like to start off by thinking, okay, what is interacting with that lamp right now? So let's see. We always know that there's the earth. That's that force of gravity that's pulling it down. But again, gravity is not an object, so we always say earth. Let's see, it's touching the table. And I don't see anything else touching it in that picture. So I'm going to draw a balance diagram that has between the table and the lamp. But we're going to be focusing on the lamp here. So here we go. Here's my little box to show my L for lamp. I just kind of go through as like a checklist. So let's do the earth. All right. So we have the force of earth acting down. We always want to make sure we label our forces. Right. And we know that one. And we were just looking at our diagram right now. We see that it is unbalanced. Right. It's unbalanced, but we know we need it to be balanced. So if there's that much acting up or down, we know we need to have the same amount acting up. All right. And we have to think about, okay, well, there's a force here. The only other thing that could be causing that force that's balancing it out is the table. Now, as people will say, like, how does a table push? It doesn't push. It's not a living object, but it is providing a push that is counteracting the force of Earth. How do I know it's pushing back up? Because because it's at constant velocity, which means we know the forces are balanced. Okay, that's it for that one. Pretty easy. All right, so let's go to number 2. All right, so we have this ball here. All right, the ball is hanging motionless from a string, which means motionless, which means we're at constant velocity, which means we know it's balanced. And then from there, we can figure out what forces we need to have act on it. So let's think, what's interacting with this ball on a string? Let's see. We obviously, like I said, we always have Earth. And let's see, obviously the string. So what I'm writing here in the green, this isn't, sorry, my pen's being a little bad. When I'm writing the green here, it's just helping me think about what's interacting with it. It's what I call a system schema. All right, this is just me thinking about what objects are interacting, what objects could be providing a force for this here. So Let's see. We have the earth. We have the string. And I think that's it. I can't. It's not touching the floor. There's no table. There's no anything else. I think we're ready to draw our diagram. All right. So let's see. We have our ball. All right. We're gonna have a force of Earth acting down on it. Now remember, it's not as play in this one as much, but how much force of Earth is acting down? The length of that arrow is going to be dependent on the mass of that object. We know it's going to be balanced forces, so we're going to be acting the same amount of force up. And that force has to be caused because we just did the Earth. The only other object that could be causing a force on this ball is the string. So the string, instead of pushing up like the lamp in the first one, this one is pulling the string up as Earth is trying to pull it down. And then I think that's it for that one. All right, let's go down to the next ones here. All right, let's go ahead and do 3 and 4. All right, so we have Sean and Dean are pushing on a box. So that, and it says system here. System means that that's the thing we're focusing on here. We'll call this one Sean. We'll call this one Dean. All right, Sean and Dean are pushing on a box in opposite directions, but the box is not moving. Again, for constant velocity, balance forces. All right. If it's not moving and it's going up balance forces, I want to think about the things that are interacting with it. Let's see. We got Earth. We got Sean. We got Dean. Let's see. What else? Ooh, it's pushing in opposite direction. The box is on the floor or ground or whatever you want to call it. It doesn't say specifically what kind of ground it is. All right. I think that's it. I can't see anything else. There's no string. There's no any other objects. All right. So I think we're ready to draw our force diagram. So there's our smaller box to represent our box. All right. I always like to just do force of Earth first. That just always makes things the easiest. Force of Earth is acting down. Now I'm seeing, okay, I need to be balanced, right? Which means there has to be an equal force acting up. And I have to look through my list of things that could be causing this force. It's not going to be Sean. Sean's not pulling it up. It's not Dean. Same thing. He's not pulling it up. The only other thing that could be acting on it, that could be pushing or pulling it up, is the floor. So you have to kind of go through a process of elimination. Okay, which one of these objects could be causing this force? All right, and then let's see. Or then we have one of them pushing it this way. And that looks like since they are both pushing, this is going to be the force of Sean. And since it is balanced, I'm going to have an equal force acting this way. This has to be then the force of Dean. Now, one thing I want to point out real quick here, when it becomes this idea of balanced forces, all right, this force right here and this force right here need to be equal with each other, all right? And this force right here and this force right here need to be equal to each other. But the blue forces and the brown forces, the forces up and down, do not have to be equal to the force left and right. Right? Just to give you an idea, like what I mean by that, let's say that this is 10 newtons. I know that this has to be 10 newtons. And this could be 15 newtons, which means I know this has to be 15 newtons. Left and right have to be equal. Up and down have to be equal, but left and up don't have to be equal for it to be balanced. All right. So number 4 is kind of the same idea, but it's a little bit tricky and adds one extra little thing to this. So we're doing number 4 now. All right. So our system is the box. We got Logan is pushing a box. which is a system, but the box is not moving. All right, I'm going to write again at constant velocity. And you're like, wow, this is really boring, writing the same constant velocity and balance every time we do this. But this helps us think about, okay, my final picture should have balanced forces. All right, so let's think about this here. We got obviously Earth. We got Logan. We got the floor. Let's see. I don't see another person. Again, there's no string or anything like that. So I think that's it. All right. So let's draw our force diagram. Let's see. We have our force of Earth acting down. Like I said, that's the one I always kind of suggest starting with first if you don't know how to get started. All right. It is balanced forces, so I know I'm going to be acting up. Oh, nope. Sorry, I did force of Earth. It's got to be one of these other objects. Well, Logan is pushing it. In this case, Logan is pushing it that way. So it must be the force of floor acting here. And then, so we got that. And then we got Logan pushing it this way. We have the force of Logan. Now, a lot of people would stop right here and say, well, there's all three of them all done. But remember, this should be balanced, which means if I have a force acting to the left and it is going at a constant velocity, I have an equal force acting to the right. And the question is, which object was it that caused this force? All right. It can't be the Earth. Can't be the Earth because the Earth only acts down. That's it. Logan is not pushing it to the right and pulling it to the left. That doesn't make sense. And it doesn't say he's doing that in the problem. It says he's just pushing it. So the only other object that this could be caused, or this force could be caused by, is the floor. Right? Which I know is like, well, wait, there's two of them here. This right here, just like how this is actually what we would call gravity, this right here is friction. Notice that the object is moving. The motion is this way, to the right. But the force of friction is acting to the left. Remember, friction always acts in the opposite direction of motion. All right? And we know it's acting the same amount as the force of Logan because it's going at a constant velocity. If Logan was speeding it up, these would be unbalanced. But again, he's pushing it when the object is not moving. So more specifically, this would be an example of static friction. Okay, let's go on to the next ones here. All right. These ones can be a little bit tricky, especially number 5. All right, I'm going to tell you right now, number 5 is a little bit tricky. All right. The answer is not as clear on it because it's a little bit tougher to kind of show. This one problem, I'll admit, is a little tougher here. So we have where our system is the rope that is between these two here. Excuse me. Right, and we have team boys and we have team girls, and they're pulling in opposite directions. We have them are competing in tug of war. The system is the center of the rope, and it is a stalemate, which means they are tied. And since it's a stalemate, no one's moving, constant velocity, balanced forces. So the same with the things that are acting on the rope here. Let's see, we got obviously boys, girls. We always have Earth. Let's see. It's not now the rope is in the air. There's no ground. There's no floor. That makes this a little bit trickier, right? I think that's it. Okay. So let's do our force diagram. R for rope. Okay, let's just do the obvious ones here first. We have a big force caused by the girls. We have an equal big force. I don't know if I drew those the same length. Those are the same length. For the boys. All right. But so we did that one. We did that one. We know there's a force of Earth. Now, rope doesn't have very much mass, so it's not going to have that much force of Earth acting down. Now, here's the problem. This is not a balanced picture. We know it's not, or since it says stalemate, it's not moving, that we have a constant velocity. All right. But I don't see any pictures here, or I don't see anything else that could act. Earth only acts down. So the only other thing that could be acting up is either the boys or the girls or both. But it has to be equal to the force of Earth acting down. So we have a little force here and a little force here. So there we go. One is the force of the boys pulling on it. The other one is the force of the girls. Oops. Girls pulling on it. And the force of the boys up and the force of the boys, girl, or these two right here. These two should be equal to each other. They should be equal to each other because it is a balanced force. So that's a tough one right there. All right, let's try number 6. Number 6, we got Julia and Grace are pushing a box in the same direction, and the box is speeding up. Speeding up. All right, here's our first one that is accelerating, which means we have unbalanced forces. Okay, so now we got to think back to the beginning of this unit. Let's think about what it means to be speeding up. Speeding up means that if the motion is this way, we have an unbalanced force. The unbalanced force must be in that same direction. All right. So here, this one was a tricky one. Let's go ahead and let's think about the things that are acting on it. We always have Earth. We have Julia. We have Grace. We have the floor. I think that's it. No string, no ropes, no what else pushing against it or pulling against it. All right, now we're ready to do our box. So first we're going to have that force of Earth acting down. All right. Then we have that same amount of force acting up because although it is accelerating, we know that it is unbalanced left and right. That's the direction it is accelerating. It's not accelerating up or down. All right. I know it doesn't say that directly, but it's implied that it's not accelerating up or down, which means that we have the force. In this case, it's got to be the floor. It's got to be the floor because Julie and Grace are pushing to the right. Earth only acts down. The only thing left is the floor. So now let's add the girls' forces, right? So there's the force of one force. There's the force of the other because they're both pushing. So we got the force of Julia. And we have the force of Grace. Now, a lot of people will be like, okay, we're all done. That's unbalanced and to the right. You are forgetting one more force. Anytime two objects are rubbing against each other, such as the box on the floor right here, we are going to have friction. Now, friction is caused by an object, and this time, the friction is not caused by Julia. It's not caused by the Earth. It's not caused by Grace, but it only can be caused by a surface. And it acts in the opposite direction. Oops, my pen's being a little challenging. Acting in the opposite direction of the motion. The motion is to the right. The force of floor, or in this case, again, just like on number 4, here's our friction. All right, there's our friction. So there's our unbalanced forces, all the forces accounted for. That is our proper force diagram. All right. Let's move on to 7, 8, and 9. Okay. So Lisa is pushing the lawnmower, but the lawnmower is slowing down. Okay, so we're doing the lawnmower this time. That is our system. All right, things interacting with that system. We obviously have the earth. We have the grass or ground. We have Lisa. I think that's it. I don't really have anything else interacting with it. Yep. Okay. Lisa is pushing it and it is slowing down. All right, it is slowing down. That's acceleration. That's unbalanced forces. But now let's think about from the beginning of this unit what it means to be slowing down versus speeding up. Her motion is acting to the right. The motion of the lawnmower is to the right. But if it's unbalanced and slowing down, all right, that means that unbalanced force must be acting in the opposite direction. All right. In number 6, the unbalanced force and motion were in the same direction, speeding it up. In number 7, motion and unbalanced forces are in opposite directions, and thus it is slowing down. That makes it a little bit trickier. All right. So it looks like it's slowing down left and right, not up and down. I don't think the lawnmower in this example is accelerating upwards or downwards. And so we know right away to begin here, we got our mower, that the forces acting up and acting down are going to be equal to one another. So there's the force of Earth. There's the force of, well, let's see. Can't be Lisa. Lisa's pushing to the right. Earth only acts down. The only thing that could be acting it would be, in this case, the grass or the ground. If you put the ground, it'd be the same thing. All right. These are the force of the surface. Okay. Lisa is pushing it to the right. So I said that right now this has to be unbalanced, and it is unbalanced right now, but as I said at the beginning, because her motion is going to the right, but the unbalanced force needs to be going to the left. All right, which means I need an unbalanced force to the left. That is a bigger force to the left. All right, and what forces are what could be causing this force? Lisa's pushing, not pulling. The earth only acts down. That would be the force of the grass or the ground acting in the opposite direction. It's still moving. Again, motion is this way, but there is a bigger force causing it to slow down. And what's slowing it down is that force of surface here, which we called earlier, we called that friction, right? But friction is not a force. It needs to be caused by an object. That object in this case is the grass or the ground. Okay, little Emma is pulling her wagon. Number 8. Little Emma is pulling her wagon. The wagon is speeding up. And so we need to find out what the system is. The wagon. There's little Emma. things interacting with it. We obviously have Emma. We have the Earth. I'm assuming she's pulling it across the ground. It's not hovering in the air. I know it doesn't say that in there, but I'm assuming that. So, okay. And we know that it is speeding up, which means we have acceleration, and it is unbalanced. All right. Now, what we have to figure out here is, again, just like in number 7, all right, her motion is, in this case, to the left. To be speeding up, her unbalanced force needs to be acting in the same direction. In number 7, they were acting in opposite directions, the force and the motion, and that caused it to slow down, the overall force. In this case here, the net force of balanced to the left and motion to the left is going to result in speeding up. So let's draw our diagrams here. Again, I don't think this wagon is accelerating up or down. So I think the wagon is going to be just fine, or it's going to be balanced forces acting up or down. There's our wagon. The forces acting up and down. In this case, they're going to be equal to one another. So there's the force of Earth. And then on the top, what force has to be? Well, Emma's pulling it to the left. Earth only acts down. So the only thing that's left is the force of ground. All right. Emma is pulling it to the left. Happy-go-lucky girl is pushing it to the left. We have the force of Emma to the left. And once again, most people would be like, okay, I'm done. It's unbalanced to the left. The motion's to the left. This is not correct right now. We have two surfaces in contact with against each other and rubbing against each other. We are missing one more force. Even though it is unbalanced to the left, there is another force acting this way. All right. There's the force of Earth only acts down. Emma's going to the left. So the only thing is that force of ground is acting twice on this object, both in the downward direction and to the right. Again, this one is what we would call the friction, because it is going in the opposite direction of the motion, because two surfaces are rubbing against each other. So now we think about overall, do I have unbalanced forces? I have unbalanced forces acting to the left. The motion is to the left. This object is accelerating or speeding up. Okay. Let's do number 9, the last one here. This one's kind of a 3-part question. All right, here we go. All right, Luke is pushing a shopping cart at a constant velocity. Draw a diagram. All right, so we've done a lot of these ones already, so I'm going to go a little bit quicker on this one here. All right, we got our diagram, we got Luke, and it says at a constant velocity at the first part here, we got a constant velocity. So there's like 3 parts here: A, B, and C. All right, for A, there's the cart. There's the cart. We have the force of Earth. We're going to have, let's see what's acting on this here. We got Earth. We got Luke. We got the floor. I think that's it, because I'm assuming there's a floor there. All right. So we have the force of Earth acting down. The force of the floor. Looks like Luke is pushing it that way. It spells fluke. And if it's balanced forces, which it says it's constant velocity, we have another force acting this way. And that's going to be our friction. If that doesn't make sense, look at one of the previous ones, either 7 or 8. I talk about friction acting on the object. And that's it. Pretty straightforward. Okay, now part B is kind of going on to the next step. He adds more groceries, but his cart is still moving at a constant velocity. The big key here is he added more groceries. If he adds more groceries, that's going to make the cart heavier. It's going to add mass. So I think it's going to pretty much be the same thing, except now with more mass, we have a greater force of Earth. But it's still a constant velocity. Sorry, a little sloppy there. All right. It's still a constant or balanced forces, which means I have to have the force the force of floor just started acting more. Well, the floor had to work harder because now there's more weight in there. So we still have balanced forces to the left and right. Luke, and our force of friction from the floor. Okay. And then number 3, Luke is in a hurry and speeds up. So his motion is going to be going this way. And since he is speeding up, that is accelerating, which means we know that we are going to have unbalanced forces for this last one. So now he's got a heavy cart that's moving quickly. So here's our cart. It's still very heavy. It's going to draw into my schema, but that's okay. There's the floor. All right. And now he is going really, really fast. So we're going to have show an unbalanced force. Right? Where the unbalanced force is greater to the left because he's accelerating. So we have the motion acting to the left. And now we have unbalanced forces acting that way. All right, to show that it is speeding up. Okay, so that goes through all of them there. Now, I know it's a long video, so hopefully you just go through the parts that you need to go through this here. All right, thank you for watching. And go back through it if you need to watch any of these other ones.